All right, so we're going to take a look at some practice problems from chapter 10. So total of 25 problems here, so let's get cracking. First one is, in the molecule shown below, determine which of the highlighted carbon-hydrogen bonds from A to E is expected to have the lowest bond dissociation energy. So lowest bond dissociation energy is going to mean weakest bond. And so the conclusion that we can draw from that is when we break that carbon-hydrogen bond, we're going to form the most stable radical, okay? So it can't be E or D. We know that because that would produce a vinylic radical. So that's a huge no-no. So then it's between A, B, and C. Does anybody have an idea which one of these is? Would it be A, B, or C that would be the weakest? These two are vinylic, so those are a huge no-no. There's one of these. If you look at A, if you pulled that off, you'd end up with a secondary radical. But like Jenny said, B and C are both tertiary, sure, but C would be the weakest bond. Why? Because it's tertiary and it's allylic. So we'll put here, it's going to be C because tertiary, let's just do this, tertiary and allylic, like that. There we go. So the answer is going to be HC. And again, if you pull that off, you could draw the resonance form of that. So there you go. So the answer is going to be HC, where HC since tertiary allylic. All right. This one here is secondary. This one here is just tertiary. All right. Next one says we'll go from most stable to least stable. So we'll put over here most stable radical. And then here we'll put least stable radical. All right, is there any of these? I was looking for a vinylic radical. They don't have any, so I guess that's off the table. But if we just describe them, we see that this one is secondary. This one is secondary and allylic. This one here is tertiary and allylic, so that's even more stable. And then this one here is primary. So if we rank them, the two allylic ones are definitely the most stable. So we go from 3, which is tertiary allylic, to 2, which is secondary allylic. Then we go down to 2, which is secondary. 1, which is secondary. And then finally 4 would be the least stable of all because it's just primary and it's not allylic. So there we go. We have the ranked from most stable to least stable. I think question number 3 is kind of a rehash of question number 1. So I'm looking for a vinylic proton. They don't have any in here. But if we just go around and describe them, HB would be secondary. HE would be secondary allylic. Then we have HD, which is going to be tertiary allylic. So we'll have here HD is tertiary allylic. HC is primary. So this one is primary. And HA would be primary allylic. So we'll put here primary allylic. Okay, so it's clear that the weakest bond is going to be the one that produces the tertiary allylic radical. So it's going to be HD. Give me a thumbs up if you're with me on this one. This is a really important question that you're able to identify the weakest bond. Okay, cool. All right, the next one, I'd say relatively straightforward. Okay, so you can see that we're taking this bromine radical. It's reacting with propane. We end up with HBr in a propane radical. So you can see what's going on here is if you draw the carbon-hydrogen bond in here, is that we're doing, we're removing the hydrogen. Not my best arrow. We're removing the hydrogen here and forming the carbon radical. And so we'd call this a hydrogen abstraction, right? Because we're abstracting the hydrogen from the propane molecule to form this secondary radical. Okay, next one, most accurate description here. So we have a double bond. We're adding a bromine radical to it. And so it's definitely not a coupling because coupling is the same thing as termination. So this is the same thing as termination. It's not a hydrogen abstraction. It's not a halogen abstraction. It's not a homolytic cleavage, right? It's not something like this. This would be a homolytic cleavage, okay? It's not that. It's the addition to a pi bond, right? We see that we're forming a bond between the carbon here and the bromine radical, and then we're forming a new radical. And so this is an addition reaction, addition to a pi bond. Number 6, which one is an example of termination? This is one that I would say students get probably 100% of the time. So termination is when you start it with radicals, and you end up with no radicals at the end, no radicals. So let's see here. The first one, we have a radical and we end up with a radical. The second one, we have no radicals and we get radicals. So this would be an example of initiation. Initiation. There we go, Mr. Dion. Okay. The next one would be a termination reaction, wouldn't it? Yes, this would be a termination because we have the propane secondary radical and the bromine coming together, and we're going to annihilate both radicals to make the 2-bromo-propane. And the next one would be a hydrogen abstraction. So this would be a hydrogen abstraction. There you go. This one here is addition to pi. That's supposed to say pi bond. All right, so there you go. So the answer is going to be C for this one. Let's see here. Which of the following are possible termination steps for the chlorination of methane? So again, termination is when we have radicals, and then at the end we have no radicals. Termination. So which one do we have radicals and end up with no radicals? It can't be this one because we have a radical and then we have a radical in the end. So it's not A. If we look at B, we have radical and radical. But if you look at C, you have two radicals coming together to make an ethane molecule. And the next one, you have a methyl radical and a chlorine radical coming together to make methyl chloride. And so C and D are both appropriate answers for termination. Two radicals coming together to make something that is a non-radical. All right, oh boy, a long question here. Free radical chlorination of ethane can produce higher halogenation products, dichlorinated, trichlorinated, etc., in addition to chloroethane. How could the production of higher halogen products be minimized? Well, we actually discussed this when we talked about the chlorination of ethane. We said if you only want to get the monochlorination product, could anybody tell me what the answer to this one is? Would you use an excess of chlorine or an excess of ethane if you only want monohalogenation products? Do you put in a lot of chlorine or a lot of ethane? Anybody know? Thanks, Isaac. Absolutely. Use an excess of ethane, and that's going to limit the amount of halogenation or polyhalogenation that can occur. Good. All right. Question number 9 is one that we haven't looked at yet, but it's a crucial question. People love to ask this question. Your instructor, ACS. So it is important that you can do it. It says, how many constitutional isomers are possible if you dichlorinate propane? So if you take propane, which is just this guy here, you treat it with Cl2 and light, okay, if it's dichlorinated. So remember, that's going to be 2 chlorines added. So what are some possibilities? Well, we could have a chlorine on the end and we could have a chlorine in the middle. We'd call that 1,2-dichloropropane. Could anybody describe another isomer that I could get besides this one? This isn't the only one. Could anybody even describe another one? Another way that I could position those chlorines, right, on my propane molecule. One possibility would be to put, thanks Jenny, would be to put both of them in the middle, right? 2,2-dichloro, absolutely. Another one would be 1,1-dichloro, right? We could have that. And then there's one more that I'm missing. So I have 3 here, but there's one more. And the other one that I'm missing is 1,3. So 1,3-dichloro. So these are all possible dichlorination isomers. There's only 4 of them, and these are all 4. Okay, there we go. All right, next one, number 10. Predict the major product upon the radical termination of tert-butyl cyclohexane. This is a great question because it brings in some nomenclature. So you've got to be able to draw tert-butyl cyclohexane, which I know you can. Okay, so you just draw a cyclohexane molecule, and then you put a tert-butyl group on it. Not too bad. So tert-butyl cyclohexane, and it says here if I brominate this, so bromine and light, well, remember that my bromine is going to go to the most substituted position. So it's going to go to the tertiary carbon, and so I end up with something that looks like this. So I'd call this 1-bromo, 1-tert-butyl cyclohexane, which is A. 1-bromo, 1-tert-butyl cyclohexane. Not my best work there. Anyhow, let's see if we can fix that up. There you go. 1-bromo, 1-tert-butyl cyclohexane. Next one just says predict the major product. Well, I think we already did this one. And just remember that once you form the bromine, once you form the radical, it's going to be the most stable radical, which is going to be this. Okay, so this is going to be your intermediate. So then when it does the halogen abstraction, you're going to end up with the bromine being in the most substituted position. So nothing really earth-shattering with that one. And there's no chiral center there to think about either. Let's see. The next one, does it... Hey, let me ask you guys a question. This is goofy. Is that a chiral center? Anybody tell me what I have circled there? This, I'll just say, is this carbon a chiral center where the arrow is? No, thanks, Isaac. It's not a chiral center, okay? There's nothing wrong with drawing it that way, but it isn't a chiral center because it's got two. This is an ethyl group and this is an ethyl group. So it's definitely not a chiral center. But you guys know that when we treat it with bromine and light, once you do the the hydrogen abstraction, you end up forming, let me use a finer tip here. You end up forming this radical, okay? And so now the bromine can come in from either face of the molecule, but again, you still don't end up with a stereocenter after it comes in. And so you end up with the bromine coming in from either face. So again, where's my bromine radical? So it can come in from either face of the molecule. So we're just going to end up with something that looks like this, where we have our bromine and our methyl group like that. And again, this is not a stereo center. And so obviously the answer has to be the only one that doesn't say RRS. It's 3-bromo, 3-methylpentane. That's all it is, right? You number 1, 2, 3, 4, 5. 3-bromo, 3-methylpentane. Okay. Number 13, predict the product. No. Okay, we got it. It says predict the major products of the following reaction. So, part of being a good scientist is thinking on your feet. And you see there's no, my knee-jerk reaction is to try to look for a tertiary position because there's no double bond. But there isn't any tertiary position in here. And you can see from the answers that it could be a mixture. Well, if you just evaluate all the positions in the molecule, you can see that this one is secondary, this one is secondary. Maybe I should do it like this. This one is secondary, this one is secondary. And keep in mind that these two carbons are identical, right? They're chemically equivalent. And these two carbons are chemically equivalent. And then this spot here, that is primary. So this is primary. So where is the major products going to occur? The bromination is going to occur at the two secondary positions, okay? Those will be the major products. So we're going to end up with B and A would be the two products that are going to be formed in the greatest amount. So we end up with A and B in this case. All right. Let's move on from there, predict the major products. So we have this compound, so it's got two chiral centers in it. And keep in mind that once we do the hydrogen abstraction, we're going to end up forming a radical. I'm going to draw the radical, and we're going to destroy this chiral center, right? This one right here, because that's where the weakest carbon-hydrogen bond is right here, because you end up with a tertiary radical. And I'll put this stereocenter in here. So put our bromine in the back like this. So there you go. So there's our carbon radical. And now we're going to do the halogen abstraction. And so we're going to end up with two compounds. And they're going to look like this. So put the methyl group here. Put the bromine. Can't see. Put the bromine there. Now what I'm going to do is copy and paste this just to help myself out in my answer. So one possibility, I'm going to have the methyl group coming out in the bromine in the back. And in the other one, I'm going to have the bromine coming out in the methyl group in back. Could anybody tell me the relationship between these two compounds? What would be the relationship between these two? One stereocenter hasn't changed, but one of them is inverted. Yeah, exactly. Thanks, Jenny. These are diastereomers. Diastereomers. There we go. Perfect. All right, next one. I can see already it involves some kind of allylic bromination because this is an allylic proton here. So we'll say here allylic. And then we're putting in a bromine in the allylic position. Now, keep in mind this is a chiral center. Even though they didn't draw a dash or wedge here, I'll help it. There we go. Now it looks chiral, and we end up with the enantiomer as well. And so what were the conditions to do an allylic bromination? So this is allylic bromination. The answer is NBS, and heat is what we use to do an allylic bromination. Okay, boy, oh boy, this one's, wow, there's a lot of possible answers here. Anyhow, it says compound A has a molecular formula of C9H20. So just some quick mental math here. The HDI is going to be 0, and probably is because none of these have any double bonds or rings. Compound A produces exactly 3 constitutional isomers upon monochlorination. Three constitutional isomers upon monochlorination, and 1 after bromination. Which of the following is a possible structure for compound A? Okay, so we're looking for 3 different sites of chlorination, so 3 different types of protons, and then only 1 spot that bromination would occur. So let's see here. So for our chlorination, we're looking for 3 types of hydrogen atoms. Okay. And then for bromination, we're looking for 1 type of tertiary carbon. Okay. Now, why can I say just 1 type of tertiary carbon? Because there's no double bond, so I don't have to consider allylic or anything like that. So let's start with the bromine. Okay. And then we'll think about the chlorine after. So let me just change the color here. So let's start with the bromine first. Okay. 1 position for bromination. Well, you can see that in this molecule, there is not just 1 position for bromination. There's no tertiary carbons, but we have secondary. Okay, so that means you get 2 isomers at least. Okay, this one only has 1 position. Okay, that where bromination would occur, right? There's only 1 tertiary position. If you're saying no, there's 2, well, the other one is identical. Okay, because remember, there's free rotation around these bonds, and so there's a plane of symmetry in this molecule. And so there's only 1 place bromination could occur here. This one, again, 2 possible places. It could occur here or here. Those 2 carbons are different. They would both yield a tertiary radical. This one, again, this one has 1, 2 carbons here and 1, 2, 3. So there's no symmetry in the molecule. And it could occur here or it could occur here. And so there's 2 different places there. Go to the next one. The next one, we have 1 place where monobromination could occur. Again, it could happen here, but those 2 sites are identical or chemically equivalent. And the last one, there's 2 different places. It could occur here or here. And so now we've narrowed it down to 2 or 5. Now, in terms of chlorination, where are places chlorination could occur? It could occur here. It could occur here. It could occur here. It could occur here, and it could occur here. So that's a total of 5 different places that chlorination could occur. So number 2 doesn't look like the right answer. But remember, there's free rotation around this bond. And note that this carbon and this carbon are chemically equivalent. Okay, so it could occur there. It could occur here, but this carbon is chemically equivalent. This carbon and this carbon are also chemically equivalent to the other blue ones. Why? Because there's free rotation around here. So far, we've only got 2 positions. It can't occur here because there's no hydrogen there. So it can't occur there, but it can occur at either one of these methyl groups, and those are equivalent. Why? Because there is a plane of symmetry running through the molecule. And therefore, the answer has to be number 5. There's only 1 place where bromination would occur. Okay. If you did bromination, you would end up with this compound, okay, here. But if you did chlorination, in that case, you could end up with, so let me just start by drawing the skeleton, which looks like this, okay? So we'll copy and paste that here and here, okay? And it's not asking us to draw them all, but let's just go for it, okay? So 1 place would be here. Another place would be here. And the last place would be on one of these. Maybe I'll just put it sideways like that. There you go. So those are the 3 places that chlorination could occur. And so the answer is V. Sorry, 5. All right. Next one. All right. Does everybody kind of follow me on the rationale for that one? I took a long time to explain it. I'm sure you would have solved it a lot faster than I did it. But give me a thumbs up if you follow me on the rationale. Right? Chlorine is available to go anywhere. Anywhere there's a carbon-hydrogen bond, it'll go there. Whereas bromine is very selective. Okay, much more regioselective. Next one involves allylic bromination. And remember that once we do the hydrogen abstraction, we're going to end up forming a radical. So after H abstraction, we're going to form this radical, which looks like this. But you know that this radical has a resonance form, and we could draw that resonance form. It's going to look like this. We're going to form a new pi bond, and we're going to make a new allylic radical, which is going to look like this. Okay, so we're going to end up with both of these radicals, and both of them can do a halogen abstraction. And so we're going to end up with a mixture. We're going to end up with this compound, and we're also going to end up with this compound. So there we go. So we end up with a mixture of these two compounds. So those are the two compounds you would end up forming. There's no stereocenters in the compounds. Let me just tidy this up a little bit. So there you go. All right. Which intermediate leads to the major product for the reaction of 2-methyl-2-butene with HBr and hydrogen peroxide? So let's see here. If we have 2-methyl-2-butene, so there's 2-butene, 2-methyl-2-butene, and then we treat that with HBr and hydrogen peroxide. Well, remember the bromine radical, okay, once we form it after the two initiation steps, is going to add to this carbon so that we end up with the most stable radical, which is going to be this, where we have the bromine here, and then we have the radical over here. Is that one of the answers? Yes, it's number 2. So there we have it. That is the intermediate that's formed along the way. Number 19, predict the products. Oh boy, this one's a Markovnikov addition because there's no peroxides in here. And so it might be advantageous for us to draw a quick mechanism. So remember, the rich are going to get richer. This is Markovnikov addition. How do I know that? It's HBr with no peroxides. And so this carbon is richest in hydrogens, and that means we're going to end up with this carbocation, and then bromide is going to come in, Br minus, like this, nucleophilic attack, like that, and that is going to give us our major product. There's no carbocation rearrangement to worry about here or anything. So that is going to be the major product. Just like that. 1 bromo, 1 methyl cyclohexane. Okay, number 20, something near and dear to my heart. Figure out a synthesis for this compound. We actually did this one earlier. If you want to make a trans diol from a cycloalkane, remember, if you're starting out with an alkane, we can cross these two off because the first step has to be bromine and light, and that is going to give me bromo cyclopentane. But then in order to put in the trans diol, I have to make the alkene. And so how am I going to do that? Well, I'm going to use a non-nucleophilic base, right? Sodium hydroxide is really nucleophilic. So I need something like T-butoxide, which is going to rip off the proton. And then to make the trans diol, I'm going to use something like step 1, MCPBA, and step 2 is going to be H3O plus, and that gives me the product. You can see the other one, this one here has osmium tetroxide and NMO, and so the answer is E. Of the 4 choices shown, which is likely to be a major product of the reaction below? Okay, so this one's going to be an anti-Markovnikov addition of HBr across our, we've got 2 double bonds in here. So what are my possibilities? Well, my radical is going to add in such a way that I end up with the most stable radical. So if the bromine radical were to add here, okay, add here, then I end up with a radical that looks like this. So I end up with my bromine, and then this guy, and something like this. So now I end up with a tertiary allylic radical. If the bromine, there's no discrimination here, right? Because both of these carbons have one hydrogen. This is the only carbon that has two hydrogens on it. So we add the bromine to the carbon that has the most hydrogen atoms on it. So that's going to be the intermediate formed along the way. Now keep in mind there's a resonance form for this. Let me just put it down here. So I'll copy and paste it down here just so we can draw both resonance forms. Okay, so we have this, and then of course we can draw the resonance form, which looks like this. So there's our curved arrows, and it's going to look something like this. So we have a double bond here. There we go, and there's our unpaired electron. So now, when we do the halogen abstraction, we can add the bromine, or sorry, the hydrogen to either of these places. Okay, we could add it here, or we could add it here. But out of these two resonance contributors, A, if we call this one A and B, well, which one's the most stable? It's going to be A because you have a tertiary allylic radical, whereas the other one you have a secondary allylic radical. And so if you do the hydrogen abstraction off of that, you end up with, so I'll just put a line here, say H abstraction, you end up with number one. So number one should be the major product, okay? Now, if you added the bromine at this position here, well, that product isn't even shown here. So the answer has to be A, or number one, A. It's the only possibility. Okay, you want to make acetone from propane. So if you're not sure what acetone is nail polish remover. And acetone is this compound here. So how do we make acetone from propane? All right, so the way that we would do that is keep in mind that acetone is a methyl ketone. And so a retrosynthesis would be, well, if I could make acetylene, then I could just do a Markovnikov addition of water across that. I would produce this enol, so I'd end up with this enol, but that enol is going to tautomerize to give me the ketone. So how do we get to the alkene? Well, we know that the only thing we can do with an alkane is to brominate it. And why would we choose bromine over chlorine? Because then you only get one product, right? So then we could do an elimination with this using a base. So it says bromine and light, so we'll use sodium methoxide as our base. So what's going on here? Bromine 2 from propane. Oh, I see. Okay, so they're doing it a little bit differently than I'm talking about here. So I was just looking at the answer, and what they're doing is they're doing the double elimination after adding two equivalents of bromine. So what they're saying is this: if you start with propane and you add two equivalents of Br2 and heat or light, that means you're going to add two bromines to the molecule. So you could either have them, they could be geminal, like this, that would be totally fine, or you could draw them as being vicinal. It doesn't matter, but they're just saying you're adding an excess of bromine. So then once you make the dibromide, you can treat that with excess sodium amide followed by water, and that's going to give you the alkyne like that. And then to get to the final product, all you have to do is treat it with sulfuric acid, water, and mercury 2 sulfate. So we'll scribble this down. Oof, I'm really running out of Taylor Swift blank space here. But let me just delete this. We'll just say, okay, we're going to treat this with sulfuric acid, water, and mercury 2 sulfate. That's going to give us this enol. And then the enol is going to undergo tautomerization to give you the methyl ketone. So I think the main thing to keep in mind here is that, yeah, if you use one equivalent of bromine, sure, you only add one bromine, but if you add two equivalents, then you can get polybromination. And since there's only 3 carbons in the molecule, it wouldn't matter where the 2 bromines were. I mean, same thing. If you were to take this compound or this compound and treat it with excess sodium amide and water, you'd end up with propyne no matter what. You'd get the double elimination, deprotonation, and proton transfer. So either one is fine. Okay, kind of a specific example, but still a good question. Number 23, propose an efficient synthesis for this one here. So we want to make this nitrile. And so we could make that nitrile from an SN2 reaction if we had this alkyl bromide, then we could just use sodium cyanide, right? And we would displace it. So we look at all of them, look, they all end with sodium cyanide, and they all start with bromine and light. Great, thanks. So let's start out by drawing the compound and saying, okay, well, if I have this and I treat it with bromine and light, I'm going to end up putting a bromine in this position. So now, in order to make this compound, I want to make the Hoffman alkene, because then I can just do an anti-Markovnikov addition of HBr across the double bond. And so for that, we're going to use a hindered base like T-butoxide, and that's going to give us the Hoffman alkene like this. Then we're going to do anti-Markovnikov addition of HBr. So I'm running out of space here, so we'll do HBr and peroxides, which gives me this compound. And then to get to the final product, I'm going to treat it with sodium cyanide. And I would pick a polar aprotic solvent like DMSO, dimethyl sulfoxide. It is polar, but it is aprotic. Okie doke. That was done. We're practically finished here. Number 24, when 2-methyl-1-propene is exposed to NBS and UV light, only one major product is obtained. How many different resonances in the proton decoupled carbon-13 spectrum are observed in the product? So if we have 2-methyl-1-propene, so if we have 1 propene and then we have 2-methyl, so another name for this compound is isobutylene. But you treat it with NBS and UV light. So NBS and light, we're going to do an allylic halogenation. So yeah, so we do an allylic bromination. So that's going to look like this. So we have the bromine over here. Then how many different carbon signals do you have? Well, there's no carbons that are equivalent here. So we have one here, 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 and here. So all 4 of those carbons are unique, and so we would see 4 signals in the carbon-13 spectrum. There's no symmetry in this compound whatsoever. With this compound, you'd only see 3, right? 1, 2, and 3. But once you add that bromine in there, you end up with 4 signals for the compound. Okay, last one. It says when you have 1,1,4-trimethylcyclohexane, it should be this. So if you have 1,1,4-trimethylcyclohexane is exposed to bromine and light, only one major product is obtained. How many distinct resonances would you see in the carbon-13? They're really hooked on these. So let's put our compound here like this. Okay, now there is symmetry through the compound, and so we would see 1 signal for these 2 guys. We would see a signal for this guy. These 2 are chemically equivalent. These 2 are chemically equivalent. This one here is unique, and this one here is unique. So we have 1, 2, 3, 4, 5, 6. And that's none of the answers. The answer is 6. Let me see here. 6 carbon-13 signals. And so the answer is going to be none of the above. I hate those where it's none of the answers. Like, that's got to be a trick. No, it's not. If you answered it correctly, it's 6 signals, and so none of the answers are on there. Or the answer isn't on there.